We're here at the famous Construction Research Lab today for a very special episode of Behind the Curtain Wall. We're here with John Medina. And George, how do you pronounce your last name?
Dotzler.
Dotzler. So we're here with George Dotzler, who leads the Construction Research Lab, basically a historic place here in Miami. It's had a lot of experience in testing a lot of curtain wall and glazing here in Miami for a lot of places around the world. So while we wait for a few people to join us, George, tell us what happens here at the Construction Research Lab.
We test basically anything that has to do with the building.
Skin.
The building envelope.
Talk to me about how, last week I came by and you gave me a great tour of everything that goes on. So how many chambers do you have here and what goes on in each of the chambers?
Well, between large and small, about 40, about 20 full-size chambers for curtain walls. And we test typically large projects because we have some very tall and wide chambers. So we have the ability to test very large mock-ups, which many laboratories can't. We also can test very odd shapes. Sometimes I'll wrap a mock-up around the corner and put it in 2 chambers. Or even we've had where we've used 3 chambers for super large mock-ups. We had one recently where we put a big inside corner in the northwest corner of the laboratory, which probably had about 80 linear feet of curtain wall.
Yeah, so the mock-ups he tests are at least for a curtain wall, 2 to 2.5 stories tall, and the objective is to capture outside corners, inside corners, parapets,
right,
and those conditions that are more susceptible to potential freeze thaw, water infiltration, structural damage from in many cases unique places in the world, such as where tsunamis can hit, hurricanes, freezing, places of that nature. And so this laboratory is in a perfect place in the world to simulate conditions like that, and so all of these mock-ups are designed in these spaces. They're like bays, right? And you could actually recreate these things. They're almost like scenes out of some movie backdrop.
Like a back lot where they have all the different sets that they can build.
And I'll tell you, George is very humble in sort of the evolution of some of these things that we're talking about. George, give me a few of the names of some of the significant projects that you've done around here.
Well, we were talking earlier, we did the Petronas Towers, and we did recently the skylight for the National Gallery, which was a reglaze of a project that we did back in the 70s, where we did 4 mock-ups for the National Galleries.
And in Florida, in Miami, Florida in particular, which is the code restrictions and requirements here are top in the country, and they guide other places in the world. Every one of the significant, many of the significant buildings back in the 70s and the 80s, the Southeast Financial Center, the original pioneering tall buildings were all tested here. Right.
Absolutely.
Espiritu Santo, which is the Miami Arch building, was tested here. I was actually a consultant while that was tested here. There was probably 4 or 5 mock-ups. RC was a competitor, but that was the first project by Permas Tolisa in the country. That was their flagship demonstration of their curtain wall. Permastelisa was started in right outside of Venice and near Vicenza.
Vita
in Italy.
Vittoria.
Yeah. So it's a really Permastelisa was one of these really high-end boutique-ish products that developed a technology of the pressure equalize and range screen system, which was terrific, right? Especially when they came out with it. And because Construction Research Laboratory is, in essence, the first of its kind, it's like a boutique-ish kind of place. It's like the best and the finest curtain walls are tested here. It's kind of like that American Express commercial where, they you don't know the person, on the card, but they happen to be best in class.
Right.
At something, and it's like, wow, I didn't realize we had that in our backyard in Medley, Florida.
Yeah, well, we're the first laboratory, and I believe we're still the largest laboratory in terms of capacity for testing mock-ups. There are larger area laboratories, but they don't have even half as many chambers as we do.
Right, and I think one of the things that I've been coming here since I worked here as a test engineer back in probably the peak sort of evolution of testing when it became really important right after Hurricane Andrew and that era of the catastrophe that happened in South Florida. The SAC, who's our mentor, George is my mentor. He was one of those people that was instrumental in the development of the large missile impact. We were just talking about that, George, a little bit about the large missile impact, how that kind of came to be, and you were bringing up some really interesting facts about how it should be, how that test should be conducted.
Well, as you were talking about SAC making a contribution, we built some test walls, and we're testing them at the initial velocities that the impact was supposed to be done at, which it was originally 88 feet per second, then 80 feet per second. But we were destroying everything. We were destroying the walls. Andrew didn't show a problem with concrete block walls. So
you're shooting out of a cannon, right? You kind of created the technology like a circus cannon, but shooting 2x4s, right?
Right. But we learned, and Miami-Dade watched with us at our experiments, that the issue wasn't concrete block walls. It was windows and doors, and especially garage doors, that could be destroyed during the storm. So kind of ignoring the wind scientists and saying we have to be rational or nobody's going to buy this, because the 88 feet per second was destroying everything, literally. We built a concrete block wall, we cured it, we stuccoed it, and then we built 3 of them, and we were testing them at the different velocities, and we basically said, well, at 50 feet per second, we won't break the wall. But at any faster velocity, we'd destroy, we go straight through the concrete block wall. And that's not what the storm revealed. So Dade County said, yeah, that makes sense. And everybody bought the 50 feet per second. We argued initially to slow the missile down because nothing that existed could pass the test. But even the wall couldn't pass the test.
And I think it's SAC. It should be said that SAC started this laboratory back in 1950, from what George was telling me.
Yeah, I was gonna say, George, could you give us a quick run through of how the Construction Research Lab came to be?
Well, SAC was a chemist working at the University of Miami after being a World War II veteran. And he finished up as a second lieutenant, and he came back to the States in the mid-40s, got his graduate degree, University of South Carolina at Charlotte, and then came back to Miami, his hometown, got a job at UM, and as low man on the totem pole, he was teaching undergraduate chemistry and working in their housing research laboratory that was doing better living through chemistry.
Sure.
And their primary focus was paints. And they had the acres of pieces of wood painted, and they would paint 2 pieces of wood, or plywood, I should say. One they'd put in the lab, and the other one they'd put out in the sun. And then they'd look at them every month or so for whatever the period of the contract was. And he'd take a picture, 2 pictures, one in daylight and one under incandescent light, so that they could compare the deterioration of the 2 samples over time. One was a
Literally watching paint
control.
dry.
Yeah, literally watching paint dry.
And you had mentioned to me when we were talking, which I actually delivered a lecture to kind of a higher selected group that the Facade envelopes, and I had said that if you found jalousie windows in South Florida, that you should hang it up because it's an antique.
Absolutely.
And that's how Sack started. Once he started the laboratory, talk to us a little bit about that.
So, in the early 50s, so Sack was working under a fellow that saw an opportunity in testing paint. So he was controlling the lab, and he went off and started doing it privately. And the university said, well, his assistant already knows what to do. Put him in charge. So Sack took over.
Go to the jealousy part.
Okay.
That's an interesting
So
part.
in the 50s, in the early 50s, we had a lot of low intensity, very wet storms. And in Miami, prior to air conditioning, everybody had jalousie windows, because jalousie window, when it would open 90 degrees to the wind. And you probably have out of every 3 inches of jalousie, only a 1/4 inch of lost airflow due to the piece of glass. So I had super great airflow. It was great when you didn't have air conditioning, but it also was glass on glass connections. And in a driving rain, you had a lot of water getting in. So the Jalousie Window Association went to University of Miami and said, here, we're going to give you thousands of dollars, and we want you to help us test our windows.
Right.
So they had this laboratory with space, and they had a guy who basically just had a graduate degree in chemistry, but he had the scientific method in his mind. And they said, hey, Sack, or, Alexander Sakhnovsky, can you come up with a way of testing windows? And it was a very basic test. He found an airplane motor. He built a spray rack, a grid with a 45-degree angle spray every 2 feet on center. He came up with 5 gallons per square foot per hour. And the first and only test was putting a window up in an archway, spraying water on it, and then blowing wind at different velocities. And the approvals weren't an approval. They were just a letter from him saying what he did and how it performed under the letterhead of the University of Miami's Housing Research Laboratory. Well, the word spread, and people were coming from all over the East Coast, especially, first for windows, and then curtain wall people who really didn't know what they were doing as they were transitioning from punched windows in masonry walls, repeating floor after floor.
So what's interesting about that for us in South Florida, which is very unique, is that at that time there was no air conditioning.
Right.
So you had to create a technology that was operable, right? So the awning window doesn't exist anymore. In fact, when you were talking about it, there's a lot of young people that don't know that it's all glass and no frame, and then you had hinges that moved the glass.
We don't even open windows anymore.
And people don't want to open windows. So then you had the awning window, right? Awning window, you still see some around, and there's, like in Hialeah and some places like that where you got these older buildings.
They're falling off the building.
The buildings, and people still don't want to replace them, right? But I think that now more than ever, right, with the changes to energy codes and requirements in South Florida, air infiltration, which is where SAC started with air and water, we've come right back around to that subject matter.
Right.
today because there is a direct correlation and connection with energy and conditioned air leaving spaces that you spend a lot of money cooling. And then at the same time, you don't want all that cold air to just go through all the cracks of your windows and doors. So the technology, and I think that and I want to emphasize it, is you guys have been continuously doing high-end testing for 74 years. Were the original developers of ideas like what's a dynamic test versus a static test where you're spraying water on a window or a door. And we were talking about it earlier. You mentioned something a little bit about, certain assemblies will do really well in static, but they won't do well in dynamic. Why don't you talk about that a little bit? I think that's kind of a curious topic.
Well, as a wind scientist and as a guy running a testing laboratory, we kind of work like a cardiologist. We get a patient, we check some basic parameters, his blood temperature, his heart rate, his blood pressure, and then the cardiologist puts him on a treadmill for 5 minutes, walking 5 miles an hour, and then he checks those things again. And he gets some kind of idea of how your heart health is. Well, so we're looking at building health. Guy comes and installs a building or a facade on a structure that we provide, and then we check its initial performance, air infiltration, sometimes air exfiltration. We'll check static water infiltration and then dynamic water infiltration. Those are all performance tests. And then we apply a stress, and the stresses include positive and negative wind loads, interstory movements, vertical, horizontal, in and out. We can do thermal testing. And then after we've done, and then, so there's the performance test, which we repeat after each stress. And then there's overstress test. So once you've defined that all the design parameters are acceptable and they continue, and the wall continues to perform, because the theory is you have a design limit and that you can beat the wall up to this design limit an infinite number of times and it will continue to perform, whether it's wind, interstory movements, temperature cycles, and it'll continue to perform. And then we go to the overload, which there's a wind overload, usually 150%, sometimes it's 200%, sometimes it's only 140%, depends on where the wall is coming from and what code is being applied. Right. And then we have over movements like earthquake 1, earthquake 2, sometimes earthquake 3. We've moved some walls for Mexico that the movement was like 6 inches plus and minus. And the criteria, as you go from design up to these overloads, like at overload, nothing can fall off the building. I mean, it doesn't have to pass air and water afterwards, but nothing can fall off the building. Whereas earlier, you had to continue to not have air leakage, not have water leakage. And you go from small movements that are maybe 3/4 of an inch to movements that are a couple inches sometimes.
And I think that George sort of talked about those things that within the industry most people know, but there are other more refined tests that are associated to, for example, swing stages. When you have a 60 or a 70-story high-rise, that you have a swing stage with 3 men on it, right? You have to tie back those swing stages, so they do a very localized test to check the tiebacks, make sure that the tiebacks won't pull out if there's an overload on the cabling, and or that there's a strong wind and you're not lifted away and you're floated away from the building, which is, by the way, happens when you'll easily get along the beach at 25 knot wind where you can't go on, right?
No, and there's wind speeds they're not allowed to work in,
right?
For sure.
And so you want to make sure that if you're traveling up and down the exterior of the building, like diehard Die Hard, one of those movies you see. You're working on the exterior of buildings, and sometimes you can't get down. You can actually see the storm coming,
Right.
and you're on the side of a building, and the wind is kicking up, and you need to be harnessed back to the building somehow. Those tests are very qualified, localized type of tests that construction research. I learned them here. I was a test engineer here for a couple of years. Zach was my mentor. He signed off on my thesis, performance of high-rise curtain walls. Actually published at, I'm a Gator, so it's published at the University of Florida. And he actually had to sign off before the faculty at the University of Florida would sign off. So they left it to Zach to say the thesis is ready. Right, and which was I'm really proud of that. That he was my teacher too.
There's nobody who knew more about it than Zach.
Yeah, Zach knew it. But I wanted to say that there are other types of tests that are very specialized, like the zipper test or a reglazing of a curtain wall. Imagine how hard it is that you have a curtain wall that was hit by a satellite dish that broke on the 50th story. How do you take that apart because the frame got damaged? And how do you take that apart and reset a frame? Well, that's a test, and it's called a reglazing test. When you do all the other tests, you go and you check, well, okay, if we were going to take this thing apart because we had some damage, how do you do it? And so those are product development type tests. And George, one of the things that we talked about back in the 80s when we couldn't keep up with the demand, this place was like a high-level glazing academy. Only the very best in the country would come here from owners like Gene McGovern, and you mentioned, in fact, that you had seen developers here like Donald Trump, people of that quality that were doing first of the kind buildings in other cities, right? They would all come here to see the final product. Architects, famous architects.
Ian Pei
was here. I met Ian Pei here one day. I went out, and very unassuming man. He was out here in the lab. You could come across 2 or 3 people and say, I just met, Bofill or Mies, and not Mies van der, that was a different generation, but Richard Meyer. I remember them.
Jeannie Gang, I met her recently.
There were no. This laboratory has seen everybody, and because there's 40 mock-ups, and you could have 40 mock-ups being tested at the same time, the degree of academic exercise and education as to how to be a scientist, and at the same time learning about material science, there's only one place in the world that could do that, and it was construction research.
No, not only that, I mean, even for, guys like us who, aren't so much in the industry, we walk in here and it's a grown-up it's a sandbox for grown-ups, right? Yeah, because you see all these chambers, you see the ability to test so many things. You see the 2 massive plane engines, you see the array that you have for sprinklers for the water testing, and then the cannon as well. Like, it's clear that from the very beginning, this was pioneering, right? And it was even to the point of how it all started.
When I was here in the late 80s to today, at the beginning, the tests were very basic compared to what we do now. There was 3 performance tests, a stress test, 3 more performance tests, and then an overload. That was a basic test. Maybe we'd include a thermal if it was from an area that was very cold. Today, there's a lot more tests that we perform. Also, back in the 80s, there was an allowable amount of water leakage. The expectation of the allowable air leakage was much higher than today. Today, Canadian walls functionally have no leakage at all. I mean, there's some of them that they're so tight, we can't even measure it with our equipment, that they're so tight. But that's because energy is expensive.
Yeah.
And it matters in Canada. It even matters in New York. but their standard, so that like the Canadian standard is 1/3 of what they use in Northern American cities, and the rest of the country is like double that again. So it goes from like 0.6 CFM per square foot to 0.01 in Canada. So
Wow.
yeah, no, they want their walls very tight.
Now, you were showing me last week a project that had just been installed where honestly I feel like it's really pushing the limits of where things are going. I mean, these glass curtain walls are getting so big. Talk to us a little bit about that. I mean, it's what, like 30 feet, right?
It's a frameless system, and it's supported with glass mullions. So it's all clear. It's all structural silicone. It has a perimeter frame, and you would technically call it a window wall. It's nominally 30 feet tall, and it's continuous around the ground floor of this building. But here we have 4 units wide with 3 fins between each of the units. And until glass breaks, it works like a beam. But after it breaks, it works like a sail. It's there curing now. It'll be interesting to see how it goes. It's a very basic test: air, water, wind, air, water overload, then impacts and cycles. The interesting thing about the impacts is they're making us break every piece of glass. Usually on an impact test, we have to hit 3 lights of glass, each in 2 or 3 places, depending on if you're a high velocity wind zone or just a normal wind zone. But we're going to deliberately break every piece of glass in this mock-up that's nominally 30 feet tall and 20 feet wide. And
so one of the things that is interesting about a frameless glass system that's a window wall and it has fins, and the fins are actually like the structure in this out of glass as well, is how much movement of that glass is something that the viewer is comfortable with. So it's not only how glass will break, but it's also what is an acceptable level of deflection, bowing, right, warping, where if you're in the inside of it and a strong wind comes, is 6 inches of movement acceptable in the center of the glass? Is 9 inches? And so the technical criteria of movement is, as long as it doesn't break, it's okay. But the psychological one as an architect,
that's something else.
As when you're an architect and you've seen glass move, and people can't necessarily visualize that. I'll tell you that I went to 2 Category 5 hurricanes in '64 as a boy, and there was the old thin profile sliding doors, and they both went over my house. It was like they were like freight trains, and I witnessed the sliding door in my house deflect as much as 6 inches because the glass was really thin and the frame could deflect and it would return back to normal. And that
was annealed glass.
And that was annealed glass.
It was probably only 1/8 inch thick.
And it was thin. And my father, who was not a scientist or a wind expert, New Yorker, figured out that he better open the door just slightly and open the door on the other side to equalize the pressure.
Wow.
Because we were going to lose the door. And of course, we didn't know any better. So we were, I was a little boy in my hand, holding on to my father and looking at my father. And he didn't, we really didn't think of the potential consequences of the glass breaking. All I know is that my dad opened the door and then ran to the other side and released the pressure, and we saved those doors for the second hurricane. All right, and I think there's something to be said about the rigidity of glass, whether it's too rigid or it's not rigid enough, right? And so as we as experts sit and look at glass, we also have to think about the bystander that is on the other side and thinking, you know, would this make people comfortable, yes or no? And I think that those are, you know, each project has to kind of go through this understanding of what's the allowable movement as what is aesthetically acceptable, psychologically acceptable. And I know, because I was out at the yard with George, and we know that lights of glass, because of the improvements in technology, the lights are becoming larger and larger, and they're becoming huge, and they suffer from other types of problems now, because now some of the stuff is brand new technology.
Right.
Right.
So then how do you navigate something where things like these glass walls are becoming more and more commonplace? Because in 10 years, it'll probably be more common to see a 30-foot pane of glass be a glass wall.
Yeah, isn't that interesting? That's one piece of glass. And in this case, it's like 5 feet wide and 30 feet tall. The largest I've seen overall was about 8 feet wide and 21 feet tall. That was for the Museum of Modern Art in New York. As new technologies develop, you don't know what you don't know.
Right.
And things happen that's why we do testing. When they design buildings, a building can move a lot more than we let it. But if people are inside the building and it's moving that much, they get nauseous. I'm a structural engineer, and we design buildings so that they don't move more than people are comfortable with. They could move a lot more and be perfectly safe. The same with the windows. They can deflect a lot and it would be acceptable. But we impose deflection limits at design, and we impose recovery limits at overload because we have decided things have to behave a certain way for our civilization to be comfortable. But yeah, when we tested to failure, as was done many years ago, we don't like to do that now. There's too much liability attached these days.
Yeah, I would just add to that because of energy conservation issues, the larger the span of glass, the subtlety in the minute deflections associated to laminating glass and having, say, 3 lights of glass in a insulated unit. So you have the outer light of glass, whether it is a tempered light, a cavity space, air space, and a laminated inboard light. That when that window is assembled on a conveyor belt sort of system, the slight deflection of the weight of the glass will create visual distortion that until you put the glass up, you really don't know how bad it could be if you're not very careful in the quality control, quality assurance processes in the plant that's making the glass. And so it's great when you have these huge lights of glass, sort of from an esoteric standpoint. Oh wow, we can build 8 foot by 30 feet. But if you walk along that glass and you look through the glass and the glasses causes distortion of what you're seeing, like, you know, in a circus where you have the mirror, you know,
the funny mirrors.
The funny mirror thing, right? It makes you look fat or skinny, or the buildings behind you too thin or too. That's a problem. So the larger the light, the more careful you have to be. You may have to beef up the lights of glass in such a way that when you lay these lights of glass flat and you start creating cavities for airspace, for energy, that glass isn't going to distort as you're putting the whole thing together and sealing it up. And that's the fine tuning part where at construction research, people produce a mock-up for performance, but they also provide many times that same mock-up is for a visual performance. What does it look like?
Sure.
And that's where the developer comes to see it. It wants to really know what they're buying.
Well, some mock-ups are Frankensteins, where they take all the odd pieces from the whole building and put them in one spot. It's like saying, okay, I want to test a human being without building a whole human being. So we got a nose, an ear, a mouth, an elbow. But then you can have a case where the tail is wagging the dog and you've ignored the dog. So a good mock-up balances both the 90% of the building and all those special details that are especially critical. And that's why mock-ups have, back in the 80s, most mock-ups were flat wall, 3 units tall, 3 units wide, but then the units were only 10, 11 feet. Now we've had units that are over 20 feet.
Right.
And that's why mock-ups went from being 3 levels to being a starter wall and 2 levels.
Right.
Because the true limitation is not what can be made, but what can be delivered. So what can you put on a truck or put on a train and move it around the country and get it up into a building? That's as big as a unit can be.
So you described it as the Frankenstein. Some projects are kind of like Frankenstein. Some curtain walls are like Frankenstein. And I've actually, I read up a little bit on Mary Shelley and Frankenstein because I had a case as an expert, as a forensic investigator. And I said, sure, you could build anything. The issue is, do you have to put a wetsuit on it so that all of the creepy goo doesn't come out between the parts of the body? Yeah, I don't have a problem that you can put a bunch of parts together. It's the gooey, ugly part that makes the Frankenstein look the way he does. Because if all he had were maybe stitches, but it's all of the stuff that's sort of creeping out, right? Well, it's similar, right? You could assemble a number of components and parts together, and you might not like the outcome of what's happening in the joinery, where either water's coming in or water's coming out, or ice is coming in or ice is coming. What condensation, vapor transmission. Years ago, one of the buildings was hit, that was hit during Hurricane Wilma. On Brickell. They replaced all of the shadow boxes in the curtain wall, right? But they took for granted that they were supposed to leave weep slots in the shadow boxes. So after about a year, when you went up the swing stage of this particular building, which is iconic, I'm not going to tell you what the name of the building is, there was an ecology that had developed in all of these spandrel panels because the condensation got trapped in the shadow boxes. About 2 inches. It wasn't leaking out. It wasn't leaking in.
Right.
The vapor inside of these shadow boxes was trapped, and it would go from hot to cold, so it would condense, the air would condense, it would become, and it built up water about 2 inches. Imagine in a 60-story building on Brickell, that you had this happening to all of these windows. It turned out that nobody checked that the weep slots at the bottom of these shadow boxes were open. And this was after a hurricane. When I saw it, it was like the most interesting experiment. What happens? You knew you're not supposed to do that, but this was a classic example of enormous amount of money to fix something, and it had to get fixed a second time.
Wow.
Well, you had a factory setting originally, and then now you have a field setting, and that's an easily overlooked detail.
Yeah.
Especially the technician is doing the job. He's just opening something, putting something back, and he doesn't know any better.
And I'll tell you, and I think I'm glad you brought up the word technician. The word has kind of gotten lost in the shuffle that anybody that's a glazer is capable of giving you solutions. There are people like George that are expert, as I am, in regards to understanding the nature of how things work and then giving solutions to problems that most people don't even begin to understand. There are many that start in the field that work their way up 20, 25 years, and I can tell you, look, they're senior guys. They could fix almost anything. Unfortunately, there are too many kind of folks that consider themselves mechanics just because they work at Jiffy Lube, but they're really technicians.
Right.
In our field, you have experts that truly can diagnose a problem, as George was talking, kind of making the analogy to medicine, and understand what that stress test is saying. There are a lot of times where you're in the field and everybody seems to have an opinion, but they haven't, like George, seen thousands of buildings or thousands of envelopes to tell you, look, I'm not just selecting a solution from 4 buildings in my life. I've seen hundreds of these, right? This is the reason why you come to Construction Research Laboratory. That's why you get specialized people. There are few in the country. I'm not going to tell you who they are. I want you to come to me, of course. But there are few people in the world that you could say, he knows.
Right.
You could trust that answer. At Construction Research, when you have a sort of boutique-ish kind of mindset, and you're really looking at product development, there are many solutions that I remember back in the 80s that worked. And then the crew of engineers and architects would say, but there's a better way. We can make it better. Let's improve on it. And I think that many of the systems that are built out there, oftentimes, they stop short of the best answer.
Right.
When sometimes the cost is pretty much the same and there's a better solution, right? So I think that's one of the advantages of a place like a CRL, where they started this business. They would continue to improve their technologies. They've had that mindset. They've taught others like me to look through the optics of a scientist like Sack. How do you look at the world? And when you've had the privilege of working under someone like Sack, Dixon Bello was another one that worked. They were partners, junior, but he was also very much engineer, very much the scientist. And they would look at the world in such a way that it gave you perspective. Not necessarily as a bystander, watching from outside the field of play, but being in the game with those that were building. And that's a whole lot different than a technician or a mechanic. That's expert.
Right.
That's being the top of class, And I have to say that having visited laboratories in Canada and other places, if CRL isn't top of class, it's tied in the country, probably in the world.
I've visited a bunch of laboratories around the world, and we've insisted on staying close to the basic science. Many people embrace very high technology, but high technology is garbage in, garbage out. If you can't go back to the basics or check things back to first principle, you can't do testing properly. And I visited one laboratory where they were doing everything electronically, and I put my water-filled manometer against it, and they were 40% overloading, and they were a factory lab testing their own product, and they wanted me to verify it. And I'm like, well, you're 40% overloading for every test: air, water, wind, everything. And as it turned out, they had an open tap in their system, so it was averaging the chamber with the environment through a small tube. So yeah, electronics is the bells and whistles are all very exciting, but if you can't go back to first principles and check yourself, it's garbage in, garbage out. That's what Sachs said directly. One of the issues that comes up that I've tried to explain many, many times is there is physical geometry is used to resist a particular air infiltration load. And that you can just look at that height, that internal geometry, and you can say, okay, you can handle so many pounds of pressure. But you go over that, the stack joint is going to overflow because you have 2 inches of static water pressure. It can only handle, your stack joint is 2 inches high. You go over 2 inches of static water pressure, it's going to overflow. And I explain this over and over, and some people just don't understand. You can't just arbitrarily take an existing system and apply higher standards without re-engineering the product. And there's a lot of people who just don't understand that.
Yeah, and I think that George is talking about something that I've had to bring up in when I've acted as an expert in a case or in a legal matter, is that that curtain walls and window walls and windows are machines, and they have to be handled as if you were looking at something that works with water, right? So the best example would be if you put the wrong oil in your engine, or you don't put enough oil, you're probably going to damage the machine.
Right.
Well, with windows and doors and things of that nature, you are expecting that the environment contributes to the performance of the assembly. And when expectations are too high, people say, well, you can finagle it to work. Well, no, you can't. You have to re-engineer it to work. I think that one of the things that you brought up, which I think is terrific, George, is early on there were no certification programs by FGIA or AMA or anything like that. It was SAC putting his signature to a University of Miami letterhead and saying, this performs at the expectation of society, and
Right.
this is fair not only in Florida but anywhere else in the country.
Basically, like almost setting the standard.
The really funny thing about that early testing is it put the Awning Window Association out of business.
Yeah.
Right. And I think that's and in fairness, it should be said that he was the precursor in establishing certifications that are accepted. That's the early version of what a notice of acceptance is in Miami-Dade County, or a Florida product approval is upstate, and so that. But in Sachs' case, being the arbitrator, being the person that understood, he wasn't recording his signature to the lowest common denominator in the design. Within reason, he would accept things that qualified as a good solution to a problem.
Right.
I think that the code, in inserting itself with certain criteria to create a common lowest denominator that would cut across every level. There's a whole lot of testing to get to that certification, that notice of acceptance. But one of the things that you do here at the laboratory is, No, you take those higher quality products that is a 30-foot span by 6 feet, or a curtain wall that's going on an 80-story, or a Petronas tower kind of thing, and you explore the best solution to a legacy project that will be around for at least 100, if not more years. And that's where you go beyond that level of master, beyond that kind of level, which takes you to the level of where Sack was when he would sign those pieces of paper.
Well, 100 years ago, people were innovating, and then the codes came along and said, this is how to do it. So most codes now are prescriptive, and people just do what is prescribed. And that's mostly killed innovation. So rather than specifying performance, they're just saying, this is how you do it. And when somebody comes along with a better idea, they're fighting the trend. It's very hard to make things better. Now, this is a problem specifically of Florida and not so much of the rest of the country, because their architects can say, I want to break the mold, I want to go further, and they're allowed to with performance expectations. But here in South Florida, it's very hard to innovate.
Well, I think that there's been some, and I'm glad you brought that up, because I think that there's and I have to create these specifications to establish what the performance level should be of tall buildings based on my 40 years of being in the business, right? So I have a fairly good record of those things, of the Iron Pay buildings, of the Beaufort buildings, and the Meyer buildings. I know those specifications. So an architect can always write a higher level of performance specification based on his understanding of a technology that you can't really take apart once it's built on a 60 or 80 story building.
Right.
And so I think that what's happened, though, that there's been bad habits created because window manufacturers want to just sort of establish the minimal criteria that's required by code. The minimum criteria established by code leads you to a level of lack of trying to kind of take it to the next level of innovation, and only getting the ticket for your, to get your laundry, right? I need the ticket for the laundry. I need, I need the cash for the hamburger, right? What is it precisely I have to do to meet the criteria? But on the Uber type projects, I think that there is that level of evolution that sort of trickles down into the sort of the lower levels that have happened. And we have to remind people that that sometimes to make a minor modification can oftentimes cost the same to get a better outcome. And I think that there's a lot of high-end developers moving towards Florida that want to see quality, that truly want to see quality. They don't want to get caught up in problems.
Right.
And then you have the kind of common thread of, we just want to meet code, and you need to place yourself in which demographic you want to be in.
No, and then obviously here at the Construction Research Lab, this is, or like you were saying, John, like this is a place where you have to exceed expectations. It's almost expected in a way. So
no, it isn't always. There's a lot of different forces involved.
Right.
My father was an architect, and through his experiences and my own experiences, I believe that every project has to stand on three legs. It has to be economically feasible, because you have to sell it at the end of the day. It has to be aesthetically pleasing, and it has to meet basic safety requirements. So it's engineering sound. There are a few projects where money doesn't matter. And these vanity projects do pop up, and sometimes engineers don't care about those other things, and they make things incredibly strong, regardless of the cost. But for the most part, they're trying to make the project stand on those three legs. So while the architect's trying to make his appearance, the builder's trying to get as little money invested as possible. So I end up with these iconic projects with the cheapest windows they can buy, because people don't look at the window, they look at the view through the window.
George, I think that happens. I think that happens until it bites them.
Yes.
It bites them in the butt because of the legal ramifications that come from things like that. But generally,
yet we test them over and over.
And generally, I would tell you that I agree with you. I think that it's there's three facets of any project that has to be dealt with, and I think that that's one aspect of it. From the standpoint of both being a consultant and an architect, in glazing specifically, I would tell you that there are understandings that exist in a proprietary spec, a prescriptive spec, or performance spec that combined together, you could get the appearance, the aesthetic, you could get the price, and you could have a quality product. Maybe it's not a vanity project, and I'm not talking about vanity projects, I'm talking about legacy projects, which is a little bit different, or architecturally significant projects that create the skyline of say, for example, Florida. Usually everyone kind of wants the same thing, quality, and the expectations that quality brings with it at the right price. The issues oftentimes happen is that things are sold as quality, and you don't necessarily get the performance you expected in the long term. You may get it in a laboratory, and there's something to be said about field testing to confirm equivalency with what's tested in a laboratory. So there's this fine, there's this balancing act of getting all of those efficiencies in installation with the product development that has in many ways been sort of cut off because of code being the most stringent in South Florida, and therefore people thinking, well, the only common denominator I have to meet is the NOA or the Florida product approval. And so what I try to do with our clients or my clients is, I look at things from that angle, but I also look at it that there's enough products that have been actually studied that bring a better quality but might be just slightly more expensive, right? And so how to bring those things and align them, and I'll have to say whether it is the lowest common denominator, where it's somewhere in the middle, or I liked your words, a vanity project, but I'll call it an architectural project, a legacy project. All of those things in glazing start in a laboratory like yours.
Yeah.
That's where it starts, and then the evolution of that through continuous sort of learning of new technologies, glass technology. You can do a 30-foot by 8-foot span of a thin lighted glass that could withstand the loads 20, 30 years ago. You can't. Well, the technology didn't exist. So laboratories, or and specifically yours, created the technology to improve on glass technology. Had there not been the testing faculties of someone like you and SAC, we would never have gotten to the place where we can make a bowed lighted glass that goes 35 feet and it's bowed and it's curved and it does all these things, and you can put it on a flat bed and move it around and it wouldn't break, right? Though all of those things are because of the improvements in technology that were done at this lab that were transferred to all the other labs, because now there's an incredible industry in testing, right? But that technology created the incredible evolution of glass technology that I'm sure would have changed the perspective of Frank Lloyd Wright and Mies van der Rohe and all of these famous architects back in the day, Walter Gropius and these guys. They would have changed the entire aesthetic of the world.
Adding new colors to their palette.
Absolutely.
I mean, there's just new possibilities that, and that's one of the privileges of working here, is seeing all these innovations. It's concave. I had a wall that was triple insulated, and it had concave and convex surfaces, and it also sloped. It was doing all of that simultaneously. The math involved was just beyond human scale. So it had to exist in this era of computers. But to actually see it, beautiful wall, amazing, and terrific performance as well.
I think that George and I are, and I've used the analogy before, is I like to see the packaging of what a building is. You know, it's kind of like Christmas when you have all these beautiful gifts packaged, you know, with bows and colorful things. And you know, as you know, every year there's one that's like, boy, I really want to get into that package because that's the great, you know, it's gift wrapped so perfectly, right? I think this is a place where, you know, young people at Macy's learn how to cut with scissors and use Scotch tape so that things look seamless, and that they won't fall apart when you're taking them from your car to your house and putting them underneath the Christmas tree. No, and we've all seen those packages done by people that you know, they're awful. It's like, oh my goodness, why didn't you just put it in a bag and hand it to me? Right? So I think that at this laboratory, like you all don't see it in the digital world, but George's eyes lit up when he was describing that curtain wall that was, you know, sloped, concave and convex and all of these terms. And when you see that for the first time, that you know that it had to be done by computers and AI, it is you know, you've just climbed out of the dark ages, right? So
in that example, one unit, it's sloping, and say it's convex or concave. Every piece of glass in that unit is a different size, because as you go out on the radius, each one's getting a little bit bigger. And now you throw in not just that you've bent the glass, you're sloping the glass at the same time. It's beyond my ability to grasp even as an engineer. I mean, perhaps a naive person can go out there and go, oh, that's nice. But I know what's involved in trying to make something like that. And I look at it in awe.
And I would just say, I would just add to, you know, we were talking about this place being kind of a university of glazing. No, and I think that you know, I'm sure that there are people out in the audience that, you know, should, you know, if you haven't been here, you should come by and talk to George, and he could give you a tour of this place, because it's a very special place, very discreet in its location. It used to be seen very clearly from the Palmetto.
Right.
And people would wonder what that place was, but they built all the way around it. So this place is now a gem amongst a bunch of new buildings.
Yeah, the world has come to us.
And so it's a very special place. So I would, you know, I hope I don't, you know, I'm not reaching too far, but
we're always happy to talk about the lab.
To talk to George here at the lab and learn a little bit more.
We've had visits from universities. UM comes here all the time, FIU. We've had people from as far away as New York come as a group from universities.
I gave years ago for the AIA back when I was teaching at the University of Miami. I gave a seminar, several seminar classes here where I would send students that were interested in glazing to get credits as electives that were at the upper level. And so I actually worked it out with SAC to have, usually we had several students and they were memorable students. Usually you remember the A students and the F students as a faculty member. And the students that I sent here were all the kind of magna cum laude types. And they had an opportunity to share with SAC some of what was going on and loved it, truly loved it. They'd come back to the laboratory and they were so excited to tell the students of how this place changed the way they saw curtain walls, right? The window walls, the architectural skin, the packaging, right? The packaging. They didn't see it as just an aesthetic, but all the parts that make up that evapotranspiration of how air and water kind of goes through the skin of a body, right?
Yeah.
So this place is definitely a university. I invite people to come meet George here at the lab. I think it'd be a great experience for.
Oh, George gave me a great crash course last week. He was giving me a tour.
One of the things I like to do is until I need an opening, I leave the old walls up because I like for people to visit and see things, and I can talk about how each job, where it came from, who the architect was, what the name of the project was, what were the innovations, and how did it perform, and we can help them understand basic terms like window wall, curtain wall, just punched openings, etc. And it goes way beyond what you kind of learn in the classroom without really understanding. Now you're seeing it, you're holding it, you're touching it.
Yeah, I think that, for example, after the lab, this lab had been here for quite a while, and I remember that I came across an engineer that was working alongside with the folks at FIU and their wall of wind laboratory, and younger fellow, and how impressed, but they could only test one at a time, right? They could only test one at a time. What has been great about construction research laboratory is you may have a unitized spandrel wet sealed system, four-sided, next to a pressure equalized rain screen barrier system, next to a precast system with gold cladded frames that's gasketed, and then and on and on and on, and watch generally the same test over and over and over again, and compare and contrast the behavior of each one of them, which is a whole lot more to be said than that you test one every so many times. It doesn't mean that there's an enormous wealth of information in regards to the wall of wind or what have you. It is the ability, and I'm very grateful to God that I had that opportunity to be here where there'd be 20, 25 mock-ups being tested all at once, and I got to deal with, as a test engineer here, with the top of the top guys making that throughout either in the United States, parts of the world like Norway and Finland and Japan and Russia, and they bring their finest people here. So not only were you dealing with I'm sure, George, you do deal with that now more than ever, but you're bringing these great assemblies that are all different types of model cars. They're different model types, right? That are first of a kind. Compare all that, and then dealing with these groups of people that were the most talented of the talented guys, talking about things like thermal cycling and acoustics and installing thermal couplings on walls to see the temperature differentials and these things. And every one of those people had an influence in coming up with the best solutions. And having that shared experience was phenomenal for me, and I'm sure it is for you, George. But everybody that comes here gets that type of experience. You can tell, you talk to a group of guys that come from Norway or Finland, and they take everything apart, put it back into their little boxes because, it's so valuable, right? And other people say, no, forget about it. You just throw that stuff away. This is plug and play, and we just need to test it for here. And other people say, wait a minute, we're going to take this apart carefully, and we're gonna leave certain things, but we're going to take other things home.
Right.
Just the nature of how a scientist deals with recycling, which is one of the other things that this laboratory it just shows, is a lot of this was made out of spare parts and contraptions and machines. I don't know if you still have, George, the two cranes that I think you guys made out of parts. There were two small cranes that were made out of parts and pieces, like those old toys that were made out of little metal.
Richard cleaned up a lot of those things in the 2000s. So we're in a new era.
Yeah.
I mean, safety is much more important than it was when we were working in the 50s. And some of the things that we were able to build and work with then just wouldn't pass muster right now. And they could be twice as strong as anything you could buy, but because they weren't certified,
I think that
they're not acceptable.
I think that they're more of the spirit that exists now when it didn't exist before. But this generation is all about sustainability and recycling, and that obsolete and old, those are two different things. And what Sack brought to in his life, he, when nobody understood who Sack was, would take parts that anyone else would have just simply thrown away, and he would make machines from them. Whereas
our cannon is a perfect example of that.
Absolutely, and it is, and it goes to show you that there was a general understanding, if you were a scientist, that recycling was a good thing.
Yes,
right?
and our cycling machine also, another example of that.
And now,
built from spare parts.
And now I'll tell you that it's interesting that new glazing assemblies, new waterproofing, new roofing, if you don't have a certain amount of materials that are reclaimed into those products, you're not complying with new energy conservation laws that are like wildfire hitting around the world, and have found themselves in Florida. In the olden days, if you said to somebody, that piece of aluminum is 100%, aluminum. It's this is the gauge, this is the type. Now, if you don't have a certain amount of reclaimed, it costs more. But you're recycling, and that's something that is as if this generation has just discovered. That this is an epiphany. Well, this epiphany exists when you see the world through the lens of a scientist. It has always been the way it should be. It's just we chose for a long time not to do it. And I think that's one of the things that Sack, his memory brings to me, is that when nobody understood what Sack was doing, making machines, sacking it, and the rest of us are better for it.
Well, we've recycled facades into our own facade, into the conference room tables. We recycle pretty much everything: wood, steel, aluminum. The only thing I have a hard time recycling is glass. Nobody wants to take my glass.
Well, so just in closing, I know that we were all kind of involved in so many different things. I would want to sort of just close with, this is a wonderful environment for sharing, and the type of technology that's being explored at this laboratory is one of a kind. I've been graced that since I want to say 83, 84 till now, I've been testing here not only as a test engineer, but I came back as a consultant, and I've had the good pleasure to deal with George and his staff. Highly professional, super sophisticated guys. They're very helpful in the design and manufacture of products. And thank you, George. I appreciate you.
Oh, thank you, John.
Meeting with me today. It's an honor.
I would agree with you, John. This place is definitely a gem. I mean, I saw it firsthand, and it's definitely a part of history in terms of architecture and engineering. Thank you, George, so much for
thank you. Thank
letting
you so
us
much.
share the time with you today. And everyone, this concludes our episode of Behind the Curtain Wall. Make sure to follow us online to stay updated on the latest.